for King Speak for parallel applications on the JVM.
So can you hear me? Yeah. Oh, so thank you for the introduction. So I'm going to talk about a new benchmark suite that we published for parallel applications on the JVM called Renaissance. So first of all, I want to talk a little bit about the motivation. So essentially, JVM is rapidly evolving. So there was a period of stagnation for some time, but now essentially there have been recently a lot of new features in the recent years, so such as concurrency primitives, various different ways to access memory, in particular lambdas, things like method handles, non-blocking I/O, and there are a lot of new features coming out like variable handles and so on. And it's kind of important in the workloads, particularly for a compiler writer, to stress this kind of actual programs which stress these workloads, right? And then, other than actually JVM evolving on its own, there have been a lot of paradigms, new paradigms, which tie into the multi-core kind of revolution, and these are data parallel programming, task parallel programming, stream processing, asynchronous programming with futures, transactional memory. So, and tied to that, there have been a lot of frameworks that people were writing, which are potentially have like a different style of programming compared to what the kind of code that was written before. So, for example, there's big data processing, there's Apache Spark, there's things like JDK, Streams, or RX, then there's frameworks like Akka for actors. There's a lot more use of Java for network communication, so there's frameworks like Netty, and a common theme in all these frameworks is somehow concurrency and parallelism. So it was very interesting for us as compiler writers to see if there are any kind of patterns, new patterns that we should actually optimize in these workloads. So essentially then what we decided to do is to gather over a period of some 2 years a lot of different new workloads, and we had several goals. We wanted to cover as many styles of modern concurrency as possible. We wanted to make the workloads as realistic as possible, so we collected workloads based on widely used frameworks, production usages that we were aware of, existing benchmarks that people wrote, which were somehow at some point interesting, but then they never actually were materialized in a benchmark suite. We even did a mining of GitHub repositories online in search for different benchmarks. And it was very important for us to stress all these different kinds of new JVM features that appeared. And one other consideration was to make the execution deterministic. Of course, if you look at parallel applications, you can only go so far in this, but we still wanted to have some sort of stable results from the benchmarks, such as like stable performance, or to have result validation, so the benchmark should always return the same value, and so on. And of course, one consideration was open source availability, because of licensing debugging and potential source introspection. And we ended up gathering around 100 workloads, and we used them to select, in the end, 21 benchmarks. And then we decided to do an analysis on them to try to get an idea, are they in some way different than these existing benchmarks which existed out there? And since we were focused on concurrency and parallelism, we chose mostly metrics which in some way correspond to concurrency primitives that you have on the JVM. So concretely, we counted the number of occurrences or invocations to a particular primitive at runtime. And based on that, we devised the following metrics. So we counted the number of invocations of a synchronized statement during the execution of the program, the number of calls to the wait method on an object, the notify methods, atomic operations, and this includes compare and swap, fetch and increment, and certain other atomic operations, then park operations. We monitor the average CPU utilization, cache misses, and we took several different kinds of cache misses and conflated them into one metric here. We tracked the number of objects allocated, arrays allocated, and then methods which have to do with dynamic dispatch. And then separately from that, we tracked the number of invokedynamic invocations. And then basically, once we collected all these metrics, so we took several steps to be able to compare them across the benchmarks. So one of the things that you can notice is like different benchmarks run for a different amount of times. So you need to somehow normalize the data. So we basically normalized the counts that we got over reference cycles with the intuition that if on average per reference cycle a certain primitive is invoked more often, then it might be more interesting for performance and might be more interesting to optimize this particular primitive. And then after that, we took a look of what's the distribution of the values, what's the mean, and then we standardized them to a -1, each of these metrics to a -1 to 1 range. So they're all now in some sort of a hypercube. At this point, we applied principal component analysis. And the thing that we found is, so it was interesting because in the first component, somehow all the metrics that represented it, or most of that represented it, somehow had to do with something that we consider features which might indicate abstractions in the program. So these were object and array allocations, and then dynamic dispatch in particular, and with this negative correspondence, there was also CPU activity. And then in the second component, we found that two of the most represented metrics with the highest correlation are the number of atomic operations and invocations of parking. So then we plotted this on these two components to see what the distribution differences are between these benchmarks that we selected and the existing benchmark suites. And what we found is very interesting. So we've now found in the existing benchmark suites, in DaCapo and ScalaBench in particular, a nice spread along this first component. But along the second component, the spread wasn't so pronounced, right? So it seems from this that, in particular, atomics and park operations are not as heavily exercised in these benchmarks. And so SpecJVM in particular was in this corner here, and this is because it doesn't have really a lot of abstraction, right? So it wasn't even very much spread along this first component, if you look at these metrics in particular. And then in the third and fourth component, a third one seemed to correspond to notify and wait calls and cache misses, and the fourth one in particular mostly to invokedynamic. And here we also saw a relatively nice spread in particular along the fourth component, and a little bit and somewhat similar to the existing benchmarks across this third component. And now if you look at individual metrics which were interesting here, so you don't look at the actual components, but you look at these metrics that we believe are the cause for this, then the thing that we saw is that we have a cluster of benchmarks here in Renaissance that essentially invoke atomic operations much more often than all the benchmarks in these existing benchmark suites. So this seems like a nice candidate for maybe taking a look at this. This might be somehow influencing performance, basically. And then another thing that was a huge difference compared to existing benchmark suites is the number of invokedynamic invocations in a benchmark. And this is not surprising given that when these other benchmark suites were made, invokedynamic wasn't basically a construct on the JVM. So you can see like in some of them there are actually some invocations, but we believe that they happen basically through a transitive call into the JDK library on a newer platform. And this is particularly interesting because this invokedynamic is used to implement lambdas and method handles, for example. And then one interesting data point is we also looked at synchronized counts. And other than one benchmark which had a heavy use of synchronized, across these other frameworks, we didn't actually find workloads which had a lot of synchronized usage, which might be an indication that developers are kind of shunning this feature, thinking that it's somehow a performance bottleneck. So despite our best efforts, we somehow selected a set of workloads where synchronized is not as represented maybe as in these other suites. So it became obvious to us that there are some differences when you look at these metrics between these benchmark suites. But what we then wanted to do as an extra step is to try to validate, can we actually change performance or see a sufficient performance difference on some of these benchmark suites with some targeted optimizations. And then being compiler writers, this is basically what we focused on. And we were able to identify several compiler optimizations that were interesting. So I'm going to talk briefly about a few of them. So one of them is extending escape analysis with support with atomic operations. So we noticed patterns in programs where essentially people either allocate a future object and then write something into a future object before publishing it, and then publish it later. And when you write to a future object, usually you use these atomic instructions. Similarly, there are these atomic reference objects in the JDK, which also get sometimes updated even though they're not shared. And if you can detect this statically, then you can optimize this. And here's one example program, very low level representation of a program where this happens. So I have a figure to illustrate this. So if you start off with an object that you just freshly allocated, and then you do a compare and swap to write another object into this original object, and then you do yet another compare and swap to make the second object point to a new value, and in the end you return this thing in the blue circle, this object B, well then, if you didn't share A with any other thread, then there's no need to execute all these expensive compare and swaps and allocations. You can immediately return B to the rest of the program. So the previous program actually just corresponds to returning a new instance of B. So this is one of the things that we did. Another thing that we noticed is that some workloads use synchronized collections. And when you use synchronized collection, you typically use it in a loop as a buffer to insert some elements into it. And then what happens is if you inline the operations of a synchronized collection, at some point during compilation, you end up with a pattern which looks like this. It's like a for loop, and then somebody calls synchronized in every iteration of the loop, and then releases it. Oops, sorry. That was a jump here. Okay. So basically, we optimize this by doing a loop-wide log coarsening. So we tile the loop into two loops, and then the inner loop is checking the same condition, but is holding the log throughout its execution, but it breaks after it does a finite number of iterations. And this helped on one of the benchmarks in particular. Another thing that was very beneficial was something that we called MethodHandleSimplification. So you have a very particular situation with lambdas in particular on JVM, in the sense that if you want to call a lambda, essentially you need to first create the lambda, and lambdas are created at runtime during the program. So code for the lambda object is created at runtime. And the way it works is essentially as follows. So first you have the invokedynamic instruction, which points to a bootstrap method, and this bootstrap method will create the lambda at runtime the first time that this invokedynamic executes. And when it executes, the lambda will be created. It'll be wrapped into an object called a method handle, and then the method handle will be allocated somewhere on the heap, and then a constant pointer to this newly allocated method handle will be replaced in the code. Will be replacing in the code this invokedynamic instruction, and then only afterwards can you do this invoke virtual call to actually call the method handle. And the way this looks in the compiler, essentially you have some control flow, then you reach the invocation, and the invocation as a first argument takes the this pointer of this method handle. And now, of course, if you have this in some very hot code, you want to inline the code inside the method handle. But the problem is, even though you know that this object is constant, you don't know actually what code it's pointing to, because a method handle itself is a wrapper around other code. So if you inline invoke on a method handle, you will be inline the code that says load something from a field and jump to a target address. But this loading from a field and jumping to a target address is essentially dynamic dispatch again. So this is one of the crucial things that we needed to add, is to do some sort of runtime reflection, where we know if a method handle is constant, then we can read this field inside the heap and then use that to inline the corresponding code directly at the lambda call site. And this was crucial for inlining, and it enabled then a lot of other optimizations. Concretely, in the Scrabble benchmark, which is a Scrabble solver written in JDK streams, it brought us some 10 to 15% improvement. Another one that we looked at was speculative guard motion. This is actually not a new optimization, but it was in Graal already. Here the point is that sometimes you have guards inside loops which don't execute in every iteration of the loop. And then you want to speculatively move them out of the loop and execute them maybe more often, and hope that they would pass anyway. But then as a result, your loop gets simpler, so maybe you manage to vectorize it later or apply some other loop optimizations to it that you otherwise wouldn't be able to. So essentially then we took these 4 new optimizations that we made and 3 existing ones, and we decided to compare them across different benchmark suites and to see what the performance effect is when enabling and disabling these optimizations. And what we found for these new optimizations, that they're much more pronounced on Renaissance than they are on this other benchmark suite, in particular, for example, handle simplification. But also, interestingly, some existing optimizations such as speculative guard motion and vectorization were a little bit more pronounced on Renaissance than on DaCapo and ScalaBench. It turns out that they were also pronounced on SpecJvm, because SpecJvm has a lot of loops. So this guard motion vectorization was also interesting there, even though it's a much more low-level suite. Another thing that we did is we compared Graal and C2 performance across these benchmark suites, and we saw a much lower variance difference on SpecJvm and on DaCapo, but on ScalaBench and Renaissance we saw like pretty large differences, and we think that Graal invests much more effort into removing abstractions in the code and doing these high-level optimizations which are responsible for these differences. And this indicates that these workloads are also maybe have like much more abstractions than this some of the more classical workloads or low-level workloads have. So one other thing that we wanted to check is the complexity of the code, because we wanted to make sure that the set of benchmarks that we selected are not some trivial benchmarks. So we did several things here. So first of all, we replicated this complexity analysis that was in the original DaCapo paper, which is called this Chidamber and Kammerer metrics, and we recorded various statistics about them. We represent, I'll not go into the details because of time constraints, but we presented the details in the paper, and our conclusion is that average are similar across the benchmark suites. What we found a little bit more interesting and maybe a simpler metric is to look at the sum of unique loaded classes across these benchmark suites. We found Renaissance has 2 times more loaded classes, but it's not very surprising because it has also 2 times more benchmarks. So it comes with 21 instead of 10 or 12. So here's an interesting metric that for us as compiler writers is indicative. So we looked at the total size of the compiled code. So something that the optimizing compiler throws out. And then we compared this across the benchmark suites. And we saw generally a nice spread, a similar spread between Renaissance, DaCapo, and ScalaBench. So DaCapo and ScalaBench in particular had 2 benchmarks which were outliers and much larger than the other ones. SpecJvm had like significantly smaller benchmarks. In addition to hot code size, we compared the hot method count, so the number of methods that were deemed important to be optimized by the VM. And here we saw again a similar distribution with a small note that it's slightly more method counts per hot method size, which might indicate that people are writing smaller methods on these newer workloads. So from this we concluded essentially that we did select workloads which are sufficiently complex and not just micro benchmarks. So then we actually open sourced Renaissance. So we made a website, documentation, we have all the code at GitHub, and we have an open source process. We're trying to get feedback from people. In particular, we're trying to get new benchmark proposals, or we want people to indicate if we maybe should somehow improve in any way the benchmark suite. So the idea is that the community can propose new benchmarks, and there's a committee that essentially, when there's a next release of the benchmark suite, tries to analyze all the benchmarks and then vote for which ones are the most important and should be included in the next release as highlighted benchmarks, sort of. And then we have next steps. We want to have a harness that gives us automatic detailed analysis of the benchmarks, not just take a look at the performance, but take a look at breakdowns of instructions, warm-up, memory behavior, and so on. And we also want to think further about compiler optimizations. And one thing that we didn't actually look into as part of this work is effects on GC and memory management. And our goal is overall to keep improving and involving the suite in an open manner. So this project was done by quite a few people. So it's quite hard to enumerate them all, but here are the pictures. Essentially, it was a collaboration between 4 universities, UC in Lugano, JKU in Linz, Charles University in Prague, and UPB in Bolivia, and Oracle Labs. So it was really a pleasure working with these people. And I think I'm out of time now, so I thank you for listening, and I'd be happy to take any questions.
Thank you, Alex. Let's have one quick question, and then we'll go for coffee. Would someone like to come and ask one?
Hi, Steve Blackburn, Australian National University. Technically really impressive stuff, and I really like your final slide there about making an open community process. So my question to you then is, how do you win over the community? Because the process that you went through wasn't actually very open. We didn't know about it until the paper was published. Right. And while that was going on, we were working with you on revisions to the DaCapo suite. So there's a question about how you rebuild trust with the community, and I just want to get a sense from you about how you're going to engage the entire community and make this open in a real sense, given that the suite itself wasn't done in that way.
Right. So I mean, it wasn't done in this way in part because we wanted to publish a paper, right? So usually, like, you work on something until you feel that it's like it's good enough that you publish it, and when you publish it, then you make it open. So this was our plan. So the release that we publish now is 0.90. So it's not like some sort of a final release. We're actually waiting for community feedback, and I mean, we're quite open to somebody saying, you know, like, this benchmark isn't good, you should remove it. So this is perfectly fine with us. If somebody can present good arguments, then we will do this, right? And in particular, if somebody has good new benchmarks to propose, we will integrate them into the suite through a completely open and transparent process. So one of the things also that we have, as I said, is this committee, which is like we try to compose it from people who are experts from different university and different places, and we value feedback from everybody who's on this committee, essentially. And one of the things is when we're cutting a new release and deciding on a set of benchmarks that we want to publish, one of the ideas that we had here is to say, okay, we do a majority vote, but fine, maybe somebody is then unhappy on the committee with publishing this particular benchmark. But in this case, a person can actually add like a paragraph to the benchmark which is published as part of the binary saying, I think this benchmark has these downsides, or is focusing on this thing too much or something. So like this public comment can be made by a committee member, for example. And
yeah. All right, sounds like you guys should have more of a discussion in the conference. Let's thank Alex and thank all the speakers in the session again. Thank you.